Hi friends, welcome once again. Now moving towards the next lecture of unit number 3rd, that is random signal and noise, let's have a quick revision. Last lecture we have seen that what is random variable, what is random process, which is also called stochastic process. We have seen that what are the differences between random variable and random process. Then we have looked what is ensemble, and we have also seen the mathematical representation of them. Today we are going to cover the topics like what are the types of random processes. Then we are going to see the each type, that is stationary, non-stationary type. Then we are going to see the statistical characteristic of random process. After that, wide sense stationary process and the mathematical representation of it. So let's start our today's lecture from the types of random process.
Random process, basically it is categorized as stationary process and non-stationary process. Stationary process in the sense whose statistical characteristic as like mean value don't change with respect to time. Example, it could be a noise process that it is not going to change depending on the time. Next, it is your non-stationary process. Non-stationary process in the sense what? Whose statistical characteristic of the random process as like mean value which is going to vary with time. So it is called non-stationary process. We have seen the example of temperature of the measurement of a city. So temperature in a particular day, it is going to be a function of time. That is the temperature in the morning, afternoon or in the evening, it could be different. So it means temperature basically it is a function of time. So it is an example of your non-stationary process. Now this stationary process, again it is classified as a wide sense stationary process, or we can say it is a weakly stationary process. The another category of stationary process is called what? Ergodic wide sense stationary process, and we are going to see one by one. In order to understand stationary process, consider this waveform. Suppose this is an instant t1 and this is an instant t2. So this is a any random waveform it is there. So what we are going to do it that we are going to measure the random variable at particular instant t1, and second random variable we are going to measure at instant t2. So the PDF, that is a power density function or distribution function, is given by small f of x in bracket x of t1. This is a first PDF, and the second PDF it is small f of x in bracket x of comma t2. So over here the statistical characteristic it don't change with time. So it means that we can also say the PDF, that is f of x t1 is equal to f of x comma t2. So we can just write as it, because it is independent of this variation in time. So it is a stationary process. So we can define stationary process as when the statistical characteristic or properties of a random process it don't change with time, it is called stationary process. Whereas when the statistical properties of a process change with time, it is called what? Non-stationary process. Now, to be more precise, consider that let the random process capital X of t, which is initiated at t equal to minus infinity. So let x of t1, capital X of t2 up to capital X of tk, they are going to denote what? Random variables, which is obtained by observing the random process capital X of t at instant t1, t2, t3 up to tk respectively. So the joint distribution function of this set of random variables, that is x of t1, x of t2, it is, we can write it what as capital F of x t1, x of t2 up to x of tk, that is f of subscript x of t1, x of t2 up to x of tk in bracket x1 comma x2 comma x3 up to xk. So make it as number 1 equation. Now let this observation interval, it is going to be shifted by amount of tau. Then new set of random variables, it would be what? Since earlier it was what? T1, T2. Now we have shifted the time by amount of tau. So it would become what? X of T1 plus tau, X of T2 plus tau, X of T3 plus tau, and so on up to X of Tk plus tau. Therefore, the joint distribution function of this new set of random variables, it would be what? Capital F of subscript x of t1 plus tau, comma x of t2 plus tau, x of t3 plus tau, so on up to x of tk plus tau in bracket x1, x2, x3 up to xk, and make it as equation 2. Now the process is said to be stationary in the strict sense if it is going to hold the following condition, right? The process is said to be stationary in the strict sense if it is going to follow the condition. And what is that condition? The condition, it is that equation 1 and 2, it should be equal. That is capital F of subscript x of t1 plus tau, comma x of t2 plus tau up to x of tk plus tau, x1 comma x2 up to xk, it should be equal to what? F of subscript x of t1, x of t2 up to x of tk, x1, x2 up to x3. So make it as equation number 3. So note it down, guys. This is one of the most important equations. So please write it down, because further we are going to use this equation number 3. So please make remember of this one. So we can say a random process is a strictly stationary if the joint distribution of any set of random variables which is obtained by the observing the random process x of t is invariant. It is what? Invariant with respect to the location of the origin t equal to 0. So it means you are going to shift the time by amount of tau or not. The distribution function, it is going to be what? Same. It is not going to vary with time. Similarly now, if there are two random processes are there, x of t and y of t, they are said to be jointly stationary if the joint distribution functions of the random variable x of t1, x of t2 up to x of tk and the random variables of second random process, that is of y of t, it is y of t1 dash, y of t2 dash and y of tj dash are invariant, that is with respect to the location of the origin t equal to 0 for all values of k and your j. Now using equation 3, so we may distinguish two situations. What are the two situations? That suppose for k equal to 1, for k equal to 1, we would have what by using equation 3? That is f, capital F, subscript x of t, x is equal to f of subscript x of, that is capital X of t plus tau function of small x, it is equal to what? Just f subscript capital X function of x, that is for all t and tau value. So make it as equation 4. That is the first order distribution function. See, it is a first order, right? We have taken this random process. So this is a first order distribution function of a stationary random process which is independent of what? Time. So that's why we have written that it is equal to what? F of x function of small x. Now consider for k equal to 2 and tau equal to minus t1. So by using equation number 3, what we would have? We would have capital F subscript x of t1 comma x of t2. Why is it so? Because k is equal to what? 2. So we have taken what? Two random variables, x of t1 and x of t2, which is a function of small x1, x2, which would be equal to what? F, capital F of x of capital X of 0. Why 0? Because earlier what we have taken x of t plus tau, but tau is equal to minus t, right now? So it would be 0. And similarly x of t2 minus t1, which is a function of x1 comma x2 for all values of t1 and t2. So make it as equation number 5. So that is the second order distribution function. Why it is called a second order? Because we have taken what? K equal to 2. Two random variables are there. So this is a second order distribution function of a stationary random process which depends only on the what? Difference between the observation times, that is t2 minus t1, not on the particular time at which the random process is observed. Now moving towards the statistical properties of random process. So first is your mean. the mean of a random process is denoted by mu of subscript x of capital X of t. So the mean value is basically is what expected value of your random process, that is x of t. So we can write it that mu subscript x function of a t is nothing but your e, that is expected value or expectation of what random process x of t. We can also write it in terms of its PDF, that integration from minus infinity to plus infinity x into f of subscript x of t, that is a random variable which is a function of what small x random variable dx. Here small f of subscript capital X of t, which is a function of small x, it is nothing but your first order power density function of your random process. And for stationary process, it is what independent of time. So we can just simply write it mu x of t is nothing but just what mu x. Now the next property is the autocorrelation function. Autocorrelation, it means what? It is what? Auto means self. So it is a self correlation which is going to be observed at a different time. It is the expectation of the product of two random variables which is obtained by observing the random process at different time. So let the random process which is observed at instant t1 and t2. So the corresponding random variables would be what? X of t1 and x of t2. So the autocorrelation function, it would be what? The autocorrelation function, it is denoted by capital R subscript this x of t1 comma t2, because we are going to observe at instant t1 as well as t2, which is given by this bar of product of this x of t1 into x of t2, or we can also say it is the expectation of the product of this two random variables, that is e of x of t1 x of t2. So we can also write it in terms of your probability distribution function that we have seen in this property mean, that expectation or of x of t is nothing but your integration from minus infinity to infinity x of PDF. So there would be two PDFs. So Rx of t1 t2, it should be equal to double integrations are there because two PDFs are there. So minus infinity to infinity x1 into x2, right? So it is a PDF x of t1 and x of t2, which is a function of what? x1 x2 dx1 dx2 with respect to this. Over here, this term, it is nothing but your second order PDF of random process, because we have observed the value at two instant t1 and t2. So we would get the two random variables. So this is a second order PDF which is going to depends only on the what? Time difference, not on the particular instant. Therefore, the autocorrelation function will be the function of time difference, that is t2 minus t1. So we can write that R, that is autocorrelation t1 t2 is equal to Rx t2 minus t1. Now the third property, it is what? Auto covariance function. Auto covariance function, it is denoted by C of x of t1 t2 subscript x of t1 t2, which is also given as this formula. that is expectation value of the product of x of t1 first random variable minus mean, that is mu x, product with this x of t2, that is second random variable, minus mu x, that is mean. Now you have to solve this term, this equation. So by solving this equation, now by solving this, so it would be of e of xt1, expectation value of this whole, x of t1 multiplied with x of t2 minus x of t1 multiplied with this minus mu x, that would become minus mu x of t1, multiplying this minus mu x into x of t2, that is minus mu x into x of t2, plus minus a minus plus, that is mu x square. By again solving it, now we have to arrange this one. So expectation value of this term, expectation value of product of this two random variables x of t1 and x of t2 minus expectation value of this minus mu x, expectation value of this x of t1 minus this mu x, and expectation value of this x of t2 plus this mu x square. Now if we would solve it, then as you know, the expectation of this product of this random variable at instant t1 and t2, it is nothing but your auto correlation function, that is rx t1 comma t2. As you know, the expectation of x of t1, it is nothing but your what? Mean. So this is nothing but your mu x. So mu x into mu x, it would become what? Mu x square minus expectation of x of t2, it is nothing but your mean. So that would be mu x. So mu x into mu x, it would be mu x square plus this term, it is plus mu x square. So by solving this, it would be what? Autocorrelation function t2 minus 2 mu x square plus mu x square, it would be what? Minus mu x square. But as we know that rx t1 comma t2, it is nothing but autocorrelation function t2 minus t1, as we already seen this one. So we can write that is rx t2 minus t1 is equal to minus mu x square. So this is the required equation for this what? Autocovariance function. It means that autocovariance function of a stationary random process also depends on what? Time difference, that is t2 minus t1. So we can write auto covariance function of a stationary random process also depends on time difference. that is T2 minus T1. Now moving towards a type of stationary process is what? Void sense stationary, or it is also called as weakly stationary process. So the process may not be stationary in strict sense. Strict sense in the sense what? All the statistical properties, they don't vary with time. But it may not be stationary in strict sense. Still, the two properties like mean and autocorrelation functions are what? Independent of the shift of time origin. Hence, over here, mean and autocorrelation function, they are constant, right? So we can write it as that mu x of t is equal to constant, right? And similarly, the autocorrelation function Rx T1 T2 is also depends on what? Depends on what? Time difference, that is Rx of tau. Over here it means, what does it mean? That expected value of x of t1, suppose expected value of x of t1, it should be equal to what? Expected value of x of t2, that is t1 and t2, both the expectation value in the sense mean, both are same. So that's why we can write it mu of x of t is nothing but your constant. So simply we can write over here, it is just what? Mu x, because it is independent of time. And similarly, autocorrelation, it is, as we have seen, that it is depends on what? The time difference. It doesn't depend on that particular instant t1 and t2. That is the expectation value of product of x of t1 and x of t2, which is equal to the expectation value of the product of x of t1 plus tau into x of t2 plus tau. So I have directly written this equation, that is autocorrelation function is Rx T2 minus T1 and tau is nothing, over here it is T2 minus T1.
So guys, in today's lecture, we have seen the types of random processes. That is, it could be stationary random process, it could be non-stationary process. Again, we have seen there are two types of stationary process, that is a wide sense stationary process and ergodic stationary process. Then we have seen the mathematical representation of stationary process. We have also seen the statistical characteristic of stationary process as like your mean, autocorrelation and autocovariance function. Here it is assignment number 9. So as usual, please note down this assignment and you have to submit this assignment. In next lecture, we are going to see that what is ergodic process and the transmission of random process through LTI filter. So if you have any questions or if you want to post any feedback, here is my email address. So here it's all about our today's lecture. Thank you very much.